All right, introduction to organic chemistry. In this chapter, we're going to discuss and define organic compounds, what organic compounds are made up of, and what different types of organic compounds in there, and finally how we can name them or formulate them. So, if we start with the term organic, organic compounds could only come from living things for the first belief for us. But when we started understanding these compounds, we studied that it is used for any carbon compound except for the very simplest. There are some kind of carbon compounds which are not included in organic chemistry. For example, carbon dioxide, for example, carbon monoxide, for example, the carbonate ions, the compound made up of the carbonate ions, and then finally the hydrogen carbonate ones. So the compounds that consist of hydrogen carbonate ions, though all of these compounds consist of carbon, but they are not included in organic chemistry. Rest all of the compounds in chemistry, which includes carbon as an element or as a part, we include them in organic compounds. Now, organic compounds can exist as long chains, they can exist as branch chains or branches, they may exist as rings, and usually carbon atoms have hydrogen atoms attached to them, but some other atoms like oxygen, nitrogen may also be attached to them. Now, moving on, when we start doing organic chemistry, we are going to face a whole lot of new compounds, different names, unfamiliar way of drawings. So don't worry, we're slowly going to get all of that. We're going to understand one step after another how to draw the structures, or how to get the structures right, how to get the names right. So we're going to go with all of that step by step. First things first, you can have compounds like straight chains. You may have branch chains. For example, this one is a straight chain. It is a zigzag-like structure. This one also is a zigzag-like structure, but there's something on top of it, all right? So we call this one as a branch. This is a straight chain. This one is different slightly. This one's different since there is an oxygen atom involved. Now, you would commonly see us using sticks to represent covalent bonds, the black balls to represent the carbon atoms, the small white balls to represent the hydrogen atoms, and we might be using some red balls to represent some oxygen atoms. That's how it is drawn. All right. Then you would
Okay.
be seeing some single straight lines. These mean single covalent bonds, right? I hope you're familiar with the single covalent bond. And if we draw two lines together like this one is a double covalent bond. So we'll be using these kinds of bonds. I hope you understand that if I talk about covalent bonds, I actually divide them into three categories. The single one, which is shown with a single line, the one that is known as a double bond, which is shown with actually a double line, and the one that is shown as triple bond, which is usually shown with a triple line, right? So we have these differences because this is the number of electrons shared from each atom. One electron shared from each atom, a single covalent bond, two electrons shared from each atom, a double covalent bond, and three electrons shared from each atom is a triple covalent bond. These are the types of covalent bond that we studied back in the very first chapters of the book. Now, moving on, we're gonna draw them, we're gonna name them, we're gonna learn all the ways to understand the organic compounds better. Now, starting with the simplest organic compounds, the simplest organic compounds are known as hydrocarbons. As the name suggests, this means they would consist of hydrogen, this means they would consist of carbon, and that's how we define them. These are the molecules which will only contain carbon and hydrogen, and no third element would be there. Now, why do we need to kind of name these compounds like this, since there are only two elements involved, carbon and hydrogen? But don't underestimate the power of compounds that are made from carbon and hydrogen, because you'll find a billion of compound and much more than that just made out of carbon and hydrogen, because the way they combine with one another, the way they can form chains or rings or branches, they can really form a lot of structures. Now, the word only is important over here. Virtually all organic compounds contain carbon and hydrogen, but hydrocarbons contain only carbon and hydrogen. which means other compounds may contain some atoms of oxygen or nitrogen or halogens or maybe some other elements. All right. So carbon atoms are joined with single bonds, double bonds, or triple bonds with one another, and with hydrogen atoms joined to them by single bonds only. So you'd notice this kind of structure in which carbon atoms are joined together in a long chain with single bonds. Or you may also see this kind of structure for double bonds. Really, for triple bonds, we don't have that many structures, but you may be able to see something like this with the triple bond. What we do right here is that we can describe organic compounds into two categories. One is saturated, that is on the hydrocarbons that consist carbon-carbon single bonds only. And the other category is unsaturated, which might contain a double or a carbon-carbon triple bond. So what would we call this kind of compound? This is a saturated compound, since in the entire structure, there are only single bonds. And this kind of structure are the examples of unsaturated compounds, because this structure at least consists of one double or one triple carbon-carbon bond. Make sense?
Okay. Yeah.
Okay, good. This is one way how we categorize them. Now, types of formulae. There are many types of formulae that we previously have studied, and we're gonna discuss them again over here, all right? So the first one is empirical formula. Now, empirical formula is the simplest whole number ratio of atoms in a compound.
Yeah, I know how to do it.
Understandable?
The yeah, I've
Okay,
done it before.
good, good. Then you must know that this kind of compound can be simplified as CH3 in empirical formula. So this
Yeah.
becomes the molecular formula, which tells us the actual state, every type of atom present, and with their actual numbers in a molecule. So I hope you understand both of these when it comes to that, right?
Yeah.
Good, good. Now, remember, empirical formula is about simplest ratio and not just the simple one, because ratio might be converted into many parts, but you're going to consider the simplest one, the smallest numbers, as small as you can. Now, molecular formulas are used rarely in organic chemistry because they don't give any useful information about the bonding in the molecule. So what we commonly do is that we commonly use them in equations for combustion of simple hydrocarbons or stuff like that. In those cases, we actually need a molecular formula. In some other cases, what we usually do is we do use a structural or a displayed formula, which brings me to the next type. We are going to go with the structural formula, but before we do that, general formulae. Now, there are many different families in organic compounds. We commonly call them homologous series. Okay, let me explain this word a little bit. Homo means same.
Yeah.
Logos actually means study. So the compounds
Okay.
that are actually look like the same or act the same, we study them in the same pattern. So homologous series is actually compounds which have similar kind of structures or which have similar kind of reactivities, so that we study them all under the same roof. For example, some families that you're going to come across are alkanes, alkenes, alcohols, carboxylic acid. These are the name of entire families. These families consist thousands of compounds, and you're going to study all of those compounds under a very few set of rules. When I use the word homologous series, it means a series of compounds. They have similar, not the exact same, but similar chemical properties. They have the same functional group. I'm going to explain what functional groups are. And each member differs from the next one by the formula of CH2, which means one carbon and two hydrogen would be different. They actually give an example so that you would know. Alkanes start off with the formula CH4. Now notice a difference of one carbon and two hydrogen is working its way for the next member in the series. The next one is C2H6. Then another difference of one carbon and two hydrogen would give us the next member C3H8. Then one carbon and two hydrogen C4H10. So that's how we work our way out. Okay, if you look at alkenes, C2H4, one carbon, two hydrogen, C3H6, one carbon, two hydrogen, C4H8. That's how we are working. Alcohols, CH4O, C2H6O, C3H8O. So you'll notice the same difference in at every step. The difference would be one carbon, and the difference would be two hydrogen at every step. And that's why he has given this kind of explanation to us. Make sense?
Yeah, yeah, makes sense.
Okay. So what do we do? Member of homologous series can be represented using a general formula. We can represent all of these by a simple general formula. For example, for alkanes, we have the general formula CnH2n plus 2. Now, if you apply different numbers, for example, when n is equal to 1, the formula becomes CH4. When n is equal to 2, the formula becomes C2H6.
Yeah,
Make
okay.
sense? So you get these formulae from this general formula. That for alkenes is CnH2n, which means the number of hydrogen atoms would be double than that of carbon. Take a look. There are 4 hydrogens when there are 2 carbon atoms. There are 6 hydrogen when there are 3 carbon atoms. So every time the number of hydrogen is exactly the double than that of carbon atom. Make sense?
Yeah, makes sense.
So every time we'll have a general formula that would represent an entire homologous series. So you're going to study different formulas at different steps. So far for alkanes, we have CnH2n plus 2. For alkenes, we have CnH2n. For alcohols, we have CnH2n plus 2O. So that clarifies just the 3 of them at this point. We're definitely going to clarify many different formulae for many different homologous series, at least for all the ones stated above. Now,
Okay.
we use the word functional group in there. So this needs a little bit of explanation. So let's explain that in the next upcoming lines. When I use
Yeah.
the word functional group, what I actually mean it from it is a specific atom or a group of atoms. What's not stated over here is that it might also mean a type of bond. And due to a single atom, sometimes maybe a group of atoms, maybe a type of bond that actually determines the chemical properties of a substance. For example, all the alcohols in the world, and alcohols are something special in the world, have this OH bond attached to them. So we call this OH group as the functional group. Because of this OH, an alcohol is an alcohol. All right.
Okay, yeah. Yeah, understandable.
So
Yeah.
all the alkenes actually have the function group C double bond C. This is the type of bond that we're discussing about. Because of this bond present in a structure, an entire compound acts like an alkene. It would have some specific properties imparted because of either this group of atoms or this kind of bond. The way of thinking about this is the functional groups is what makes the behavior of a particular compound different from that of an alkane. All right. So
Yeah. Yeah.
functional groups actually make them something special or something different from the rest of the homologous series. So functional group can be a single atom. It can be a single atom such as chlorine. It can be a single atom such as bromine. It can be a group of atoms like this, OH. It can be a type of bond like double or triple bond between carbon or atoms or carbon or some other atoms, right? So we are going to use this word for different series. Every homologous series will
Okay.
have a different functional group, but the entire set of members from that homologous series will have the same functional group as we defined above. Moving on,
Okay.
structural formulae is how the atoms in a molecule are joined together. There are two ways we can draw their structures. For example, displayed formulae. Displayed is also known as a full structural formula. In this formula, what we do is that we draw all the atoms and all the bonds. Take a look. You would notice that we have drawn all the atoms of this compound C4H10 as well as all the bonds. At every single step, you'd be able to notice what kind of bond there is between all the carbon atoms and all the hydrogen atoms. You would be able to see every single bond there is, right?
Yeah.
Uh, are you asking a question? I didn't get that.
No, no, no. I have to say yeah or whatever because I have a throat ache kind of, so I can't really respond well. So, but I want to know that I'm still here.
All right, understandable. Okay, so remember the displayed formula would be a formula in which there should be all the atoms and all the bonds. You cannot skip any single bond. Okay.
Okay.
For example, there
Yeah.
is a compound C2H5OH. Now, sometimes I've seen students doing this, drawing the
Okay.
whole structure. Now, you would notice every atom and every bond has been drawn. But sometimes I've seen students making this specific mistake.
Yeah.
Now, if you do this, I hope you notice that the difference over here, and let me clarify, this bond, this OH single bond has been shown, and this bond has not been shown over here. So once they say the word displayed formulae, you need to show all the atoms and all the bonds, and one bond is missing over here. And actually, Edexcel tends to cut marks at this point. If we don't show all the atoms and all the bonds for the displayed formulae, that's not right. That's not the way it should be. All
Yeah.
right.
Yeah.
Now, displayed formula may also show you a ball and stick model for a diagram, which actually shows you all the atoms. As you can see, first carbon atom, second carbon atom, third carbon atom, fourth carbon atom, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogen atoms. So you can see all the atoms. And since they
Yeah.
are all
Okay.
singly bonded, they are all connected to one another. If there was a double bond, there must have some longer sticks used in the structure. So you would know. So displayed formula is the one which can show you what's really going on in a molecule in terms of covalent bonding and in terms of actual number of atoms present in there. Okay. Now,
Yeah.
an important reminder, it's important to remember when you draw structures, carbon always form 4 bonds, hydrogen always form 1 bond, oxygen is going to form 2 bonds, and any halogen like fluorine, bromine, or iodine are going to form 1 bond. All right. So you
Yeah.
should remember the number of bonds an element is going to form. If you remember the number of bonds, you're always going to make sure that you draw the formula right. Okay.
Okay.
Now notice, since we say that carbon always form 4 bonds, so look at this carbon, it's forming 1, 2, 3, and 4 bonds. Look at this
Yeah.
carbon, the second carbon, 1, 2, 3, and 4, right? So you would be
Yeah.
able to actually calculate that whether you have drawn the bonds right or not, which
Yeah.
is pretty important in this case. Okay, so I'm going to move on and we're going to study more. So how to draw a structural formula. For any other than the smallest molecules, drawing a full displayed formula is very time consuming. So what we can do is displayed formula has one more category. Now the structural formula, sorry, the structural formula has one more category and we call it the condensed formula. We may emit
Okay.
carbon-carbon single bonds or we may emit carbon-hydrogen single bonds. Now I'm going to give you an example. This structure is actually shown like this.
Okay.
Okay, so I'm going to draw all the atoms and all the bonds so that you would know that this is a displayed formula. Now I'm going to convert this displayed formula into this condensed kind of formula. How do we do that? Okay, so I'm going to mark it in an easier way. We take one carbon and all of its hydrogen and we write it like this, CH3, right? Since this carbon is
Yeah.
connected to 3 hydrogen, and then the next
Mhm.
carbon, and then the next carbon, and we keep going on, and we keep writing the number of hydrogen atoms with it. We can either write it like this. Now, if you want to also omit these single bonds that we have written over here and here, you can simply write it like CH3, CH2, CH3, like this. Both of these are known as condensed formulae. All right. Condensed means we have
Yeah.
contracted them a little bit for the ease of writing. Now, this is a method that has been adopted by almost all the scientists or researchers or teachers or students on the planet. So it's actually makes the whole thing easier for us to write. We are quicker, we are more efficient, and we're actually displaying the whole thing without even drawing any bond signs. So you can pick any of these methods. Now, this method means that we have omitted all carbon-hydrogen bonds, but we have drawn carbon-carbon bonds. This method means we have omitted both the carbon-hydrogen bonds and the carbon-carbon bonds. You can pick any of these methods, this one, or both of them omitted, whatever you like. All of these are considered correct. But when a question is asked in a specific way, let's say he asked a displayed formula from you, then you should know that this is not the type that you're supposed to do. This is the displayed formula. These are the condensed formula. And when he keeps
Okay.
the question open-ended, when he leaves the choice for you, then you can choose any of the methods to write them. It's entirely up to you then. And most of the time in the paper, he's going to leave the choice open to you, which is actually a pretty great thing since the students can write the way they find easy. They may show the whole displayed formula. They may just omit the carbon hydrogen single bonds. They may omit all kinds of bonds at all and simply write the most condensed form of the formula. So it completely depends on the student then if it's an open-ended question. Coming to how to draw the structural formulae. So you can simplify the formula by writing like this or this, as I just explained. So you'd notice this is the condensed way of writing when you are writing the carbon-carbon bonds. This is the condensed way of writing when you are not writing any kind of bond signs or single lines, be it carbon-carbon bond or carbon-hydrogen bond. Now, this is still showing the exact number of carbon and hydrogen atoms, but it also shows us how the formula goes, how the structure goes. This is the molecular formula. This definitely does not show us anything about the structure, but this one or this one does. So that's why they're named as structural formula. And this one is named as molecular formula. Because if it gives you any hints about the structure, it definitely is a structural formula. All right. So when I talk about this structure, take a good look. This is C4H10. This is one CH3, one CH2, one CH2, and then another CH3 on the other end. So it can be written like this. You may write it like this. You may fold it like this. It remains the same thing. No matter how you fold it, it remains the same molecule. So you can write it in any ways possible and it won't change. We usually write it in this way. It's just the manner of explanation that you may twist it as you want to. Make sense? Okay.
Yeah.
Now, that does make sense. Okay, a couple of key points. If you're asked to draw the structure for a molecule in IGCSE exams, you draw it as a displayed formula. Now, why do we go with, or why are we favoring displayed formula? It's that you can't lose any marks by doing this. You might lose any marks if you use the simplified form because you might make a mistake. But if you are drawing the whole displayed formula, you're definitely gonna go with all the atoms and all the bonds, and you will be confident that you're doing it right. But again, it's just a key point. You may prefer any version of it. Now, it's entirely up to you whether you prefer writing this way, you prefer writing this way, or you prefer writing, drawing the whole diagram, displayed formula like this one, right? So it's
Yeah.
entirely up to you which one you choose. Moving on. The best way to understand that these are all the same is to make some models. If you don't have any access to molecular models, you blobs of modeling clay joined together with pieces of matchstick or small nails, and you can change the shapes by rotating around the bonds. This is actually what happens in real molecules. So you can actually rotate the structures. Now, this structure This structure that we have shown you in a straight line can be shown like this zigzag pattern. This structure can be shown like this. This structure can be shown like this. So the ball and stick models can actually also be rotated just like these structures. That's why we ask you that you should know how the simple structure can be twisted, but actually it remains the same molecule that we have been talking about since the start, C4H10. So all of them is actually the same thing. And that's what he told us in the hint. Now, the structure formulae may be drawn in various ways. Sometimes no bonds are shown, other times some bonds are shown. Easiest way to think about this is like this. If all the bonds are shown, then it is a displayed formula. And if not all of them are shown, and you can still see what the structure is, then it's a structural formula. If you simply jot down all the number of all the atoms, it's a molecular formula. It's not a structural formula anymore. Why? It's not going to help you with how the structure is. Okay, so that's a very good difference between different kinds of structural formulae and the molecular formula. Moving on, a molecule like propene, the formula of which is C3H6, it has a carbon-carbon double bond. Now, it can be shown by drawing two lines for the double bond, and the rest of the hydrogen atoms can be shown. Now, you can show this displayed formula in different ways again, since the structure can be molded or bended in different ways. Now, you can draw it like this. If another student draws it like this, even then he or she is correct. Now, you'd notice that this structure and that structure is the same. Both of them are C3H6. It's just a difference of drawing. You may also write it like this or this. So it's entirely up to you. Okay.
Yes.
But usually when we write it like this, we try to show the double bond. You may write it like this, but it's better if you show the double bond. Okay.
Yeah. Okay.
Even in the condensed form. So in the condensed form, you may omit the single bonds, but it's better to show the double and the triple bonds.
Okay.
This is all about showing how the molecules are. Now let's start working towards their names. Naming organic compounds is different from naming inorganic compounds. Now we have studied how to name inorganic compounds. You know, we always name the metal first or the positive ion first. We name the non-metal after. We add to their oxidation states in their names if they belong to transition elements, so on and so forth. We had different rules for naming of inorganic compounds. So when we talk about organic compounds, the naming rules are a little bit different. Their names are different. The prefixes or suffixes are different. I mean, the parts of the name. And each part of the name has a specific purpose, tells something specific about the molecule. So you're going to understand what every part of the name means. And you're going to make sure that you name it accordingly. So the naming rules are met, and actually naming rules are in place so that everyone can easily understand the structure from the name, or from the structure, the name. All right. So it's entirely up to us that we can work it both ways. Okay. Now, code letters. Code letters are actually prefixes or suffixes of the name. I hope you understand, even for human names, we have like several parts. We say what's the first part of the name, or what's the last name, or maybe what's the surname. We have different parts of the name for us. In organic chemistry, the names are actually divided into prefixes and suffixes. Prefixes are usually the starting parts of the name, and suffixes are usually the ending or last part of the names. These are all prefixes.
Yeah. Okay.
Okay, these are going to come to be the starting parts of names, actually, starting parts of the parent name, if not any other part of the name. And they are actually going to represent number of carbon atoms in the chain. Now, we have seen different structure. There can be one carbon atom in the chain. There can be two of them. There can be three of them. There can be four of them, or there can be hundreds of them. So we have a naming criteria that we follow. All right. So what I'm going to do is that we're going to go with naming criteria given over here. and we're going to do something extra as well. So if there is one carbon atom in the chain, we're going to go with the prefix meth. Two carbon atoms, eth, three prop, four bute, five pent, hex is for six, and I'm going to write hept is for seven, oct is for eight, non is for nine, and dec is for 10. Since we're going to go as high as 10, even at this IGCSE level, so I asked my students to go a little extra mile, and instead of just the first six code letters, let's go with first 10. We're going to use them later anyhow. Okay. So make sure you write them, and when you're done writing, let me know. I can erase them and move forward.
Yeah, sure.
Okay, good, good. So what does that mean? We actually help with mnemonics. For the students, mnemonics sometimes are really helpful. They help them remember. So monkeys ink, eat pink bananas. It's a way to remember meth, eth, prop, and bute, 1, 2, 3, and 4. Pent means 5, hex means 6, so they are very easy. You can also remember them from pentagons and hexagons, the structures in mathematics. I hope you understand that pentagon had 5 corners and hexagon had 6 corners. So those shapes had the
Yeah.
names because of the words in place. All right. So moving on. Now, for example, butane, the word bute means 4 carbon atoms. Propane, the word prop means 3 carbon atoms. Now, to coding for the type of compound, when we come with this heading, we're actually talking about the last name. Or in other words, we are actually talking about the suffixes. All right. So when the prefixes and suffixes combine, you can actually form the whole name. So let's talk about the suffixes. Now, the suffixes really depend upon the homologous series that we are studying. Every homologous series has a different set of suffix. For example, alkanes are a homologous series of hydrocarbons forming only from carbon and hydrogen. In this, the carbon atoms are joined with single covalent bonds. That's why we said alkanes are saturated hydrocarbons, since they only have single bonds. And the suffix that we use is ane, A-N-E. For example, if there is a 2-carbon chain and they're singly bonded, we'll use the word ethane. Now, this name makes a perfect sense, since eth tells us that there are 2 carbon atoms. Ane tells us that those carbon atoms are singly bonded. That's how actually organic chemistry has every part of the name set in place for a specific reason. Moving on to another family homologous series, alkenes. It's also a hydrocarbon homologous series that only consists of carbon and hydrogen, but they are based upon carbon-carbon double bond. The name ends in E-N-E. For example, ethene, we're going to use the same thing, ethene. Eth means 2 carbon atom, 1 and 2. Ene means they're doubly bonded, this one. Right?
Yeah.
So the double bond can be in place in different points in the longer chains. Take a look at the longer chains. This one is butene. Now, name should be butene, right? Since bute means 4 carbon atoms, ene means there must be a carbon-carbon double bond. That doesn't mean all the bonds are doubly bonded. That just means there would be at least one double bond in the structure. And we usually study the compounds that have one double bonds. There are compounds that have multiple double bonds in the structure, more than one, maybe 2, maybe 3, maybe more. But we only study the ones which have one double bonds to make it easier for the student. Now, butene is actually named a little bit differently. Notice, if the double bond is at the start of the structure, it's but-1-ene. And if it's at the second carbon, if the double bond starts from the first carbon, it's but-1-ene. If the double bond starts from the second carbon, it's but-2-ene.
Okay.
Which means the 4-carbon chain with the double bond starting on the first carbon, the 4-carbon chain, the double bond starting on the second carbon. That's how actually we name them. All right. Naming is going to be a little bit difficult than this. I'm just starting off with the basic rules of your book. I'm definitely going to use the whiteboard to explain more complicated names. For example, there is a hint. In complicated molecules, presence of the code N in the name shows that the carbon are connected by single bonds, all right? So for example, propane 1-ol means, prop means 3 carbon atoms, N means singly bonded, 1-ol means ol is actually a functional group. We're going to explain it later. 1 means the function group is connected at the first carbon atom. So we're going to do it in the upcoming chapters, don't worry. This and this structure has been drawn over here. This structure, however, no, actually, no, that's not it. This structure has been drawn over here and he's trying to show you the same structure, but with just the difference that we have to number the structures in order to get the same thing, right? Means the structure is sideways or numbered like this, the structure is sideways or numbered like this, but actually they are the same structures. Both the single bonds, actually double bonds, actually start from the first carbon atom. Take the look, the double bonds is in between the carbon atom number 1 and 2. The double bond is in between carbon number 1 and 2. So actually we number the carbon atoms and the numbering starts from the end, whichever produces the smallest numbers for the double bond. I'm going to explain that a little later since this comes difficult to students if not appropriate examples are given. Okay, both parts of this figure are the same molecule. It's just that if the molecule has been turned over from left to right or from right to left, vice versa, it would be silly to change the name every time because the molecule moved. So both forms are known as but1-ene. So we're going to explain that a little later too. So coding for branch chains. We're going to go for all the codings first, and then we're going to combine it to see how the names form. All right. So coding for the branches. When it comes to the hydrocarbon chains, they have side branches on them. For example, this is a simple hydrocarbon-based compound in which all the carbon atoms are in the straight line and the hydrogen atoms are surrounding them. All right. Little bit of a poor drawing over here. They shouldn't be intersecting it, but it's just a manner of speech. It's just drawing. Now you may notice something like this where all the carbon atoms are in the straight line, and you may notice something like this where all the carbon atoms in the straight line, but there is a branch going on with carbon atoms also drawn or connected to the internal carbon atoms. We call this as the parent chain, and we call this as the branch, right? Just like the branches on the trees. The trees try to go up, but the branches try to scatter at different points like this, right? The branches try to scatter all the way to get as much sunlight as possible, right? So we call these branches. Although this was a straight line, but some branches came out of it. The similar thing happens with the organic chemistry. Make sense? Now, the branches are coded in the same way. If there is one carbon atom, we're going to use the word meth. If there are two carbon atoms, we're going to use the word eth. But the suffix is different. The suffix is not "ene." We're not going to use that, or "ene." That's not it. We don't use them. Instead, we have a separate suffix of "I." So meth becomes methyl, eth becomes ethyl. This single bond shows that the branch can be connected to any structure, any parent chain. Now notice the count of numbers comes before the suffix. So of course, the count of numbers is going to act as a prefix most of the time.
Yeah.
Okay. Now, the name of the molecule is based on longest chain. They've actually started naming. Just give me a moment. Okay. I guess now we need the naming rules. So for the naming rules, let's go to the whiteboard. Since I won't have enough space over here, So I won't be able to explain to you the different set of rules that they have posed over here, since almost every paragraph over here explains one rule. So let's take the help of a whiteboard and explain it over there. Okay. So I'm going to stop sharing over here and I'm going to share a whiteboard with you. I hope you're able to access the whiteboard.
Yeah.
Okay. Now this whiteboard is filled up with heating and cooling curves. Let's get them. Let's go for the last page. Now, can you see a clear white page?
Yeah.
What can you see in front of you?
Rules of naming
Okay,
organic.
good. That means my screen has been shared perfectly. So now we're going to go with rules of naming, and I'm going to explain rule by rule by giving you different examples so that it's easier for you to understand. And while we're explaining the rules of naming, I'm simply going to go with alkanes first.
Okay.
All right. So
Okay.
I'm going to go with alkanes first. Let's start with the most basic rule. As soon as you see a chain in front of yourself like this one,
Okay.
now this one is pretty easy to name, right? How?
Yeah.
How many number
It's
of carbon atoms are there?
there. Wait, hold on, sorry. There are 4.
So we name it with bute. And
Yeah,
what kind
but
of bond is there in between the carbon atoms?
single bond.
So ane.
So it's
Easy
butane.
enough.
Yeah.
Butane, right?
Yeah.
Let's change the example a little bit. Okay, how many carbon atoms are there?
There are 6.
So that is named as hex.
So,
And again, they're all singly bonded. So
yeah,
hexane,
hexane.
right?
Yeah. Yeah.
This seems to be pretty easy. What
Yeah.
happens is that when there is a branch in the structure, the entire set of rules change. Okay. Then you actually need to understand and identify. You might know that on the previous page, I was telling you that this one is the parent chain, and this one is the branch, right? Just because
Yeah.
they are all in a straight line and this one is on top. Okay, I accidentally wrote brain, not branch. Okay, this is actually branch. Okay, so this is the branch. So just because they're all in a straight chain and this carbon is present on top as a separate portion, this becomes the parent chain, this becomes the branch. No, actually there are some set of rules in place because of which this is known as the parent chain and this one is known as the branch. So we're going to start with those rules. What are those rules? The first rule is to locate the straight. Straight means all connected, longest. My bad. Seems to be making too many spelling mistakes today. Carbon chain.
Okay.
So there can be multiple straight longest carbon chains, right? Okay, let me clarify. What do I mean when I use the word multiple? This is the first straight longest carbon chain since it consists of 4 carbons. There can be another way by which we go. This can be a straight longest carbon chain, and this also has 4 carbons, right?
Yeah.
Okay. Whether we pick this one or we pick this one, we can work with both the ways, and you get to see that the second point actually helps us with it. Number the carbon chain starting from carbon where branch is connected gets the lowest possible number. Now, we're going to number the carbons. There are multiple ways to do that. We can number this carbon in first, this one as second, this one as third, and this one as fourth. All right.
Yeah.
We can go the other way around. We can number this one as first, this one as second, this one as third, this one as fourth, right?
Mm-hmm.
This is the carbon where branch is connected in case of black. So if this gets number 2, this is correct. If this gets number 3, this is wrong. So this numbering is wrong. Remember,
Okay.
the carbon where the branch is connected should get the lowest possible number. So this carbon is the most important one. This should get the lowest possible number. If it gets number 3, that's not the right numbering. If it gets number 2, that's the right numbering.
Okay.
Let's go with the red kind of numbering. In case of red, this can get first, second, third, or this can get fourth, or this may get first, or this may get second, this may get third, this may get fourth. In the case in which it gets second, this carbon where the branch is connected, this becomes the branch in case of red. Number 2 is correct, number 3 is wrong. So it means this kind of numbering is incorrect, and this kind of numbering is correct.
Yeah.
Now, let's come to our final rule, the third and last rule, naming.
Yeah.
Naming is done in this way. Number of carbon atom. I don't have enough space over here. So what I'm going to do, I'm going to erase the upper portion.
Yeah, no, I don't mind. I already wrote it down.
And I'm going to write the rules over there since I would have enough space to easily write the rules over there. Okay. So the third rule is name it like this. Number of carbon atom at which branch is connected hyphen, then just a second. Okay. Then comes name of branch, then name of parent chain. All right. Name of branch and name of parent chain are not separated by any ways. However, this number is separated with a hyphen or a dash. Okay, take a look. Whichever numbering we pick, whether the black or the red, the number of the carbon atom at which the branch is connected is 2 in both cases. That's the best part of it. Any kind of numbering the child can come up with, you're going to wind up with the exact same number, right? Then comes the dash. Actually, the dash is used to separate the letters and the numbers in organic naming. Now, 2 was the carbon atom at which the branch was connected. Now, the name of the branch has single carbon atom. So meth would be the prefix and il would be the suffix, as I explained on the previous page. Remember, the branches have the prefixes same as the parent chains, meth or eth or prop or but, right? But the branches have the suffix of il. Al goes for branch, right? And ane goes for the alkane or the parent chain, right? So 2-methyl, and then there are 1, 2, 3, 4 carbon atoms in total. So that is but and ane. 2-methylbutane would be the complete name. Now, every part of this name plays its role. Okay, let me clear that
Yeah.
out so that it's easier for you to know. So I'm going to clear all of this out so it's easier for you to see and know. Oh, I accidentally cut the wrong parts out, but I'm going to redraw it anyway. Okay, so it was CH3, CH2, CH3, right? This was the parent chain, this was the branch, remember. Okay, 2, my bad, this 2 was there. So 2 represents that on the second carbon atom we have the branch. Meth represents the branch has 1 carbon atom. Al represents the suffix of the branch. But represents that there are 4 carbon atoms in the parent chain, and ane represents all those 4 carbon atoms are singly bonded. So every single part of this name actually gives us the idea of the entire structure. If you're going to follow these rules for the names and these prefixes and suffixes for how to put the words together, then you're going to get every time the name right. Also, the names are going to keep you safe from the different kinds of bending and twisting of structures, because when we bend and twist structures, it's difficult to understand whether the structures are same or different. It only works if we are able to come up with the same name. All right.
Okay. Yeah.
Now, since it's about time, so I believe that we should stop right here.
Yeah.
Okay. And we'll continue from the same place.
Okay.
Right.
Yeah.